Something is changing on Jupiter. Not suddenly, not violently, and not in a way that can be understood at a glance. It is happening slowly, across years and even decades. But the scale of that change is enormous. Because Jupiter has always represented something different. It was never just another planet. It was the constant, a world of endless storms and flowing clouds that seemed chaotic, yet followed patterns so stable they felt permanent. For generations, astronomers believed that while Jupiter was dynamic, it was also predictable, that its behavior would remain consistent once understood. But that assumption is beginning to break, and what is replacing it is something far more complex. A system that is not fixed, but evolving. Jupiter is the largest planet in the solar system, with a mass more than twice that of all the other planets combined. That mass gives it real influence, shaping the motion of objects across vast distances and acting as a gravitational anchor for the entire system. But what makes Jupiter truly unusual is not just its size, it is its structure. Unlike Earth, Jupiter has no solid surface, no ground to stand on, no continents or oceans in the traditional sense. What we see is only the upper layer of a vast atmosphere made mostly of hydrogen and helium. As you move deeper, pressure increases to levels that completely change the behavior of matter itself. Under those extreme conditions, hydrogen transitions into liquid metallic hydrogen, a state where it behaves like a metal and conducts electricity. This layer plays a critical role in generating Jupiter's powerful magnetic field, like the strongest of any planet in the solar system. Jupiter also does something unexpected. It emits more energy than it receives from the Sun. This excess energy comes from deep within the planet, generated by leftover heat from its formation, combined with ongoing gravitational compression. That internal energy drives powerful convection currents, where hot material rises and cooler material sinks, keeping the atmosphere in constant motion. Unlike Earth, where weather is driven mostly by the Sun, Jupiter is powered from within, and that internal engine fuels its storms. For centuries, those storms appeared stable, violent, but consistent. The most famous of them all, the Great Red Spot, became a defining feature of the planet itself. First observed in the 17th century, it has existed for at least 300 years, a massive storm large enough to swallow Earth. It rotates with immense energy and was long believed to be a permanent structure in Jupiter's atmosphere. But that belief is now being challenged. The Great Red Spot is shrinking. This is not speculation. It has been carefully measured over time. In the late 1800s, the storm stretched nearly 40,000 kilometers across. Today, it is less than half that size, and its shape has also changed, becoming more circular and more compact. Its outer edges are no longer stable. Fragments appear to break away and are pulled into surrounding jet streams, where they eventually dissipate. This suggests something important. The storm is losing energy. And the fact that this is happening now, after centuries of persistence, raises a deeper question. Why would a storm that lasted so long begin to weaken? To understand this, we have to look beyond the storm itself. Because on Jupiter, storms are not isolated events like they are on Earth. They are part of a much larger system connected to internal heat, atmospheric chemistry, and powerful jet streams that circle the planet. So when a major storm changes, it may not be a local event, but a signal that something deeper is shifting. In 2016, NASA's Juno spacecraft entered orbit around Jupiter, designed to study the planet up close. It passes within just a few thousand kilometers of the cloud tops, collecting data with unprecedented detail. And what it has revealed is changing our understanding of Jupiter. One of the most surprising discoveries came from Jupiter's poles. Instead of chaotic storm systems, Juno found structure. At the North Pole, the 8 massive cyclones surround a central storm. At the South Pole, 5 do the same. These storms are stable. They maintain their positions. They do not drift randomly or merge into one another, forming organized patterns unlike anything observed on Earth. This suggests that powerful forces are maintaining their structure, forces that are still not fully understood. Jupiter rotates extremely fast, completing one full rotation in under 10 hours. This creates strong Coriolis forces that shape atmospheric motion in extreme ways. But even that may not fully explain what we are seeing. There may be deeper processes at work, linked to how energy moves through the planet and how its internal structure behaves. Juno also revealed something unexpected about Jupiter's atmosphere. Its iconic bands do not extend as deep as once believed, and they reach only about 3,000 kilometers below the cloud tops. Below that, the planet behaves differently, with the deeper interior rotating more like a solid body. This suggests Jupiter is layered, not just in composition, but in motion. And that boundary between layers may be influencing everything happening above. This changes how we understand the planet. Because if Jupiter's structure is more complex than we thought, then its behavior must be as well. The shrinking of the Great Red Spot, the stability of polar cyclones, and the shifting patterns in its atmosphere are not isolated events. They are connected, part of a larger system that is still revealing itself. What we are seeing is not instability. It is not randomness. It is a planet evolving, responding to internal forces, adjusting over time, and then slowly exposing the deeper mechanics that drive it. Because the truth is simple. Jupiter was never truly still. We just couldn't see it clearly before. Everything we observe on Jupiter is only the surface. The clouds, the storms, the bands, even the Great Red Spot, all of it exists in just a thin outer layer of an incredibly deep planetary system. What lies beneath those clouds is far more important and far more difficult to understand. Because Jupiter hides its true nature. Unlike Earth, where we can study the surface directly, Jupiter offers no such access. There is no solid ground, no place to land, no direct way to observe its interior. Everything we know about what exists below the clouds comes from indirect measurements. Gravity, magnetic fields, radiation, subtle changes in motion. And when scientists began analyzing this data through NASA's Juno mission, they realized something unexpected. Jupiter's interior is not behaving the way they thought it would. A magnetic field that doesn't make sense. Jupiter has the strongest magnetic field of any planet in the solar system. It is not just slightly stronger than Earth's. It is dramatically stronger. So powerful that it extends millions of kilometers into space, creating a vast region known as the magnetosphere. Within this region, charged particles are trapped and accelerated, creating intense radiation belts that would be deadly to unprotected spacecraft. For decades, scientists believed they understood how this magnetic field was generated. It was assumed to be relatively smooth and predictable, created by the motion of liquid metallic hydrogen deep within the planet. But Juno revealed something very different. The magnetic field is not uniform. It is uneven, distorted, irregular, and in some regions, it is far stronger than expected. One of the most unusual features discovered is known as the Great Blue Spot. This is a region near Jupiter's equator where the magnetic field is significantly stronger than surrounding areas. But what makes it truly important is not just its strength. It is moving, slowly but measurably. A core, that may not exist. For a long time, scientists believed that Jupiter had a solid core, a dense center made of rock and metal, similar in concept to Earth, but far larger. But recent data suggests something far more complex. Jupiter's core may not be solid at all. Instead, it may be diluted, spread out, mixed with surrounding material. Rather than a clear boundary between core and atmosphere, there may be a gradual transition, a fuzzy region where heavy elements are distributed over a large area. This idea challenges traditional models of planet formation. Because if Jupiter does not have a well-defined core, then the way it formed may be different from what we assumed. It may have experienced violent impacts early in its history, or processes that redistributed its internal structure over time. And if that structure is still evolving, then Jupiter may not be as stable as we thought. The energy problem. Jupiter's energy output remains one of its most important characteristics. It releases more heat than it receives from the Sun. But what is becoming increasingly clear is that this energy is not distributed evenly. Some regions of the planet appear more active than others. Some areas show stronger convection, more turbulence, more storm formation, while other regions appear relatively calm. This uneven distribution suggests that the internal flow of energy is complex and possibly changing. And if energy flow changes, everything changes. Storms, winds, atmospheric structure, even long-lived systems like the Great Red Spot, waves in a giant atmosphere. Recent observations have revealed something else. Waves. Not waves like oceans on Earth, but atmospheric waves that move through Jupiter's cloud layers. Some of these waves stretch across thousands of kilometers. They maintain their structure over time, traveling through the atmosphere in ways that are not fully understood. Others appear suddenly, then disappear. These waves may be linked to deeper processes within the planet. They could be the result of internal oscillations, or interactions between different atmospheric layers, or even changes in energy flow from the interior. On Earth, atmospheric waves can influence weather patterns. On Jupiter, they may be shaping entire regions of the planet. Lightning where it shouldn't be. One of the most unexpected discoveries from Juno involves lightning. On Earth, lightning occurs primarily in equatorial regions, where warm, moist air rises and creates storms. Scientists expected something similar on Jupiter. But that is not what they found. Lightning on Jupiter is more common near the poles. This was completely unexpected. Because the poles receive less solar energy, they were assumed to be less active. But instead, they show strong electrical activity. The explanation appears to involve ammonia. Jupiter's atmosphere contains ammonia clouds, which behave differently from water clouds on Earth. Under certain conditions, ammonia can combine with water ice to form what scientists call mush balls. Soft, hail-like particles that transport material deeper into the atmosphere. This process may be more active near the poles, leading to increased storm activity and lightning. Again, a pattern emerges. Something deeper is influencing what we see above. A system under constant adjustment. Taken individually, each of these discoveries is significant. But together, they tell a larger story. Jupiter is not a simple system. It is not a stable, unchanging giant. It is a dynamic environment where multiple processes interact at once. Internal heat, magnetic forces, atmospheric motion, chemical interactions. All of these are connected, and all of them appear to be evolving. What we are witnessing is not a planet breaking down. It is a planet adjusting, responding to forces that operate on scales far beyond anything we experience on Earth. And those adjustments are becoming visible. The limits of our understanding, Perhaps the most important realization is this: nothing happening on Jupiter is impossible. There is no violation of physics. Every observation can be explained using known scientific principles: fluid dynamics, thermodynamics, magnetohydrodynamics. But understanding those processes at Jupiter's scale is incredibly difficult because the interactions are complex, non-linear, and often hidden beneath layers we cannot directly observe. Jupiter is not mysterious because it defies science. It is mysterious because it pushes science to its limits. A planet still revealing itself, Jupiter is not finished. It is not complete. It is not a system that has settled into a final state. It is still evolving, still adjusting, still revealing new aspects of its behavior. And with each new observation, our understanding changes. What we thought was stable turns out to be dynamic. What we thought was simple turns out to be layered. What we thought we understood becomes something deeper. The shift becomes clear. The shrinking of the great red spot, the shifting magnetic field, the unusual lightning patterns, the structured polar storms, the complex internal layers. These are not separate mysteries. They are connected. They are signals of a system that is more active, more complex, and more dynamic than we ever imagined. And this leads to a deeper realization. Jupiter is not just changing. It has always been changing. We are only now beginning to see it clearly. What is happening on Jupiter is not just about Jupiter. It is not just about storms or magnetic fields or strange atmospheric patterns. Because when a planet this large begins to reveal unexpected behavior, it forces us to look beyond it. It forces us to ask a bigger question. What if our understanding of giant planets has always been incomplete? For a long time, Jupiter was treated as a reference point, a model, a baseline for how gas giants behave. Scientists assumed that if you understood Jupiter, you understood similar planets across the universe. But now, that assumption is starting to shift. Because Jupiter is not as simple as we once believed. It is not a static system. It is not fully predictable. It is something far more complex. And that realization changes everything. A new perspective on giant planets, Jupiter, is often described as a typical gas giant. But in reality, it may be anything but typical. The discoveries from the Juno mission suggest that Jupiter's internal structure is layered in ways we did not expect. Its magnetic field is uneven and evolving. Its storms behave differently from what models predicted. Its energy distribution is not uniform. And all of this points to a deeper truth. Gas giants are not simple spheres of gas. They are dynamic systems shaped by interactions between heat, pressure, rotation, and chemistry. And those interactions can produce behavior that is far more complex than we once imagined. If this is true for Jupiter, then it is likely true for other gas giants as well. The connection to distant worlds. In the past 2 decades, scientists have discovered thousands of planets beyond our solar system. Many of them are gas giants. Some are even larger than Jupiter. These planets orbit other stars, often under very different conditions. Some are extremely close to their stars, exposed to intense radiation. Others exist in colder, more distant regions. But until recently, our understanding of these worlds was based largely on what we knew about Jupiter. We assumed similar physics would apply. And in many ways, it does. But Jupiter is now showing us that even familiar